Hi students, in this lecture I am going to discuss problems based on oblique collision. Let us see first one. A body of mass m makes an elastic collision with another identical body at rest. Show that if the collision is not head-on, the bodies go at right angle to each other after the collision. So collision is elastic but not head-on, identical bodies, and one is at rest. So we have to show that they go at right angles to each other after the collision. Let us see carefully. So not head-on means it is oblique collision. So one body is moving and one is stationary. Let us say its velocity is u. Another identical body is given that is at rest, stationary. So the condition is that if velocity is not along the line joining centers, collision becomes oblique. Okay. So now see what we can do here. Let us take the line joining the centers. Line joining the centers. Let us join the centers. Suppose this angle is theta. Now take for velocity two components. So one is along the line joining centers. That is u cos theta. Other one is normal to that. That is normal to that. It is u sin theta. See the line joining the centers, that is a common normal. Okay. If you focus only common normal, collision is head on. Okay. For the time being, leave this u sin theta. For the time being, leave it. Now focus identical bodies. Collision is elastic. In head on collision, they exchange their velocities. So this is what we have discussed in the previous lectures, right? Identical bodies, when collision is elastic and head-on, they exchange their velocities. That means after collision for the first body, along the common normal direction, velocity is zero. That means it becomes now along common normal, no velocity, zero, and this will be along common tangent. This remains the same. That won't change, remains the same. The relation is that force by first one on second one or by second one on first one is only along the line joining their centers. There is no net force along the common tangential. That's why this component does not change. And coming to the next one, the second one, its velocity. It is u cos theta. So now we can say directly u sin theta and u cos theta. These two are mutually perpendicular, right? This angle is 90 because we have taken components along the line joining, normal to line joining. These two are mutually perpendicular. Keep this result in mind. So when collision is oblique and identical masses, one of them at rest before collision, then after collision, between their velocity vectors, angle will be 90. Okay. Let's see next one. See the question given. A ball of mass m hits a floor with a speed v, making an angle of incidence theta with the north. The coefficient of restitution is e. Find the speed of the reflected ball and the angle of reflection of the ball. Right, see how to calculate this. Given speed is v, angle of incidence theta with a normal. So coefficient of restitution is given, that is e. We have to find speed of reflected ball and angle of reflection. Right. See that first of all, given condition with a normal, it makes angle theta. Its velocity is v. Suppose this is after collision velocity v dash and this is theta dash. So we have to find v dash how much and theta dash how much given coefficient of restitution. Right. So here you can see one is earth. Right. So I'm taking this body which is moving as a first object. Earth is now second object. Then we can write coefficient of restitution E equal to V2n minus V1n upon U1n minus U2n. So I'm taking ground as second body. Therefore, its velocity 0, V2n 0 minus V1n. This is V dash, right? Let us take sign convention here. Suppose up as positive, then see V dash cos theta dash, that is a positive. V dash cos theta dash positive upon U1n, that is V cos theta downwards negative minus V cos theta. Minus minus gets cancelled. It is now V dash cos theta dash upon V cos theta. This is one condition we got. So we have two unknowns, V dash and theta dash. So we require now one more equation. Actually, in the question, they have to mention that between the object and the ground, there is no friction. In that case, along horizontal, momentum does not change. In the sense, you can say velocity components. When there is no friction, velocity components along a tangent does not change. So I can write here it is V sine theta, velocity component along a tangent before collision should be equal to velocity component after collision. Assumption is that there is no friction. Okay. So we got two equations and two unknowns. Now we can solve it. See what we can write in the place of V dash by V. V dash by V sine theta by sine theta dash. That means E equal to sine theta by sine theta dash. This is a cos theta dash by cos theta. See from this, what is this? This is a tan theta upon tan theta dash. So from this, we can write tan theta dash is equal to tan theta upon E because we have to calculate angle of deflection, right? This value. Next, we have to find the value of V dash. Since we got the value of theta dash, we can find the value of V dash, right? So here key points. So one is writing coefficient of restitution. Then we have to focus velocity components along the common normal. Its meaning is along which line impulsive force acts. Okay, that is what we have taken. Next condition, along the tangent, there is no friction. Therefore, velocity components remains the same. Okay, let us see next one. Let's see the question carefully. Two identical balls are in contact on a table or in equilibrium. A third identical ball collides them simultaneously, symmetrically, and remains at rest after impact. The coefficient of restitution is, see how to calculate now, coefficient of restitution. So mainly we have to focus on how we are taking components along the common normal. Okay, let us make a diagram. Given two identical bodies which are stationary on a horizontal surface, the third identical one making collision now symmetrically. It is actually symmetrically. So velocity take it as u. Symmetrically means if you join the centers of these three balls, that makes equilateral triangle, right? Now see what we can say. For example, this is x-axis. Initially, these two balls were at rest and this third ball was moving. Therefore, writing LCM, law of conservation of momentum, along x-axis. Okay, then see what happens. By symmetry, we can say their velocities after collision will be along the common normal direction. Take it as V. So how to identify means join their centers now in this case. So this is the direction or this is a line along which impulsive force acts. So those two balls will move along their common normal direction like this, right? Then see what I can write here. Mu should be equal to, after collision, this is a coming to rest. Okay. So coming to for remaining two, I have to take components along x-axis. This angle is, that angle is 30, right? We can see total angle is 60. If I am joining centers, this is 30, this is 30. So this is also 30. So mv cos 30, mv cos 30. Now same thing second ball, I'm taking into 2. So m gets cancelled. The relation between v and u, or this is equal to cos 30 root 3 by 2. 2 gets cancelled. This is now, I take here 2v root 3 by 2. 2 gets cancelled. Now next one, we have to calculate coefficient of restitution. In that case, we have to focus only components along the line joining them. Sorry, components along the common normal direction. That means we have to focus along this line or along this line. Let us take this is a first body. This is second body. We can focus either these two balls or these two balls. Okay. So I'm taking now these two balls. Now write here coefficient of restitution V2n minus V1n upon U1n minus U2n. Okay. V2, I'm taking this as second body. V2n is nothing but V because its velocity is along common normal. This is V. So follow very carefully why how we are taking components. V1n after collision first body coming to rest. So 0 upon U1n. Before collision for first body velocity was U along x-axis. Take its component along the common normal. This is now 30. So cos 30. It is U cos 30 minus 0. For second ball before collision velocity was 0. Then see what we get. V by U cos 30. So V by U cos 30 means root 3 by 2. Okay. See from first equation, in the place of U, V root 3 in the place of U. In the place of this substitute, in the place of that substitute, V root 3. V gets cancelled. It becomes now 2 upon 3. That is now coefficient of restitution. Okay. So focus carefully how we are taking components along the common normal. If you are knowing that, you can solve question. Let's see next one. See the question carefully. A small sphere of mass 1 kg moving with a velocity 4 cap minus j cap meter per second. It hits a fixed smooth floor and rebounds with velocity I cap plus 3 j cap meter per second. The coefficient of restitution between the sphere and the floor is. See here, we have to find out velocity components. Okay, let us see how we calculate. So first of all, write down the given data. Mass is given 1 kg. Anyhow, mass is not required to calculate coefficient of restitution. Find velocity. So u bar before collision velocity u bar equal to 4 cap minus j cap meter per second. After collision velocity equal to, it is I cap plus 3 j cap meter per second. So we are given velocities before collision and after collision with the flow. Okay. And we are knowing that coefficient of restitution V2n minus V1n upon U1n minus U2n. Okay. Means we want velocity components along the common normal. Right? See how to, for example, this is a floor. This is a common normal velocity. This is u bar and this is v bar. We want their components along the common normal. Okay. Then see what I can do here. We are knowing that change in velocity vector will be along a common normal. You can see along the floor there is no force. So along the floor there is no change in velocity components. So force is now normal to the floor. Therefore, velocity changes only in normal to floor. Therefore, I can write here delta V bar change in velocity vector that is equal to I cap plus 3 j cap final value minus initial value 4I cap minus j cap. See how much we get? I cap minus 4j cap. That is minus 4. This is minus 3I cap. 3j cap minus of minus plus 4j cap. Okay. We want for this velocity vectors components along the common normal. Okay. Let us take this as direction n cap. So n cap is direction of n cap given by delta v bar by modulus of delta v bar. Okay. Because velocity changes only along the common normal. Therefore, this is minus 3I cap plus 4j cap upon modulus value is 5. Right. Now focus carefully how to find components. To find components. Remember while learning vectors, right? Taking components. So we want a component of u bar along common normal. So I'm taking u bar dot n cap. So whenever we want a component along one direction, we have to take dot with a unit vector, right? Let us see what we get here. U bar dot n cap. 4I cap minus 3I cap. So it is minus 12. Minus 12. Minus j cap plus 4j cap, right? It is minus 4 upon 5. This is minus 16 upon 5. This is a component of u bar along the common normal. Okay. And you can see here directions are opposite, right? That's why we got here negative sign. Okay. Means angle is 180, right? We take the component. Next. Focus V bar dot n cap. See how much V bar dot n cap? I cap dot minus 3I cap. That is minus 3. 3j cap dot 4j cap. That is plus 12 upon 5. It is 9 upon 5. And you can see this is a positive because its a component is along n cap. Okay. And its a component is opposite to n cap. See, one is velocity of approach, other one is velocity of separation. That's why one is a positive and one is negative. Okay. So coefficient of restitution is modulus of velocity of separation by modulus of velocity of approach. This is now 9 upon 5. Velocity of separation, velocity of approach 16 upon 5. So answer is 9 by 16. Okay. I hope you got clarity how to find velocity of separation and velocity of approach. So first finding n cap. How to get it means velocity vector changes only along n cap. Okay. See the next one. Right. See the question carefully. A ball is projected with a velocity v naught, that is root gh, at an angle theta to the horizontal towards a smooth vertical wall, distance d from the point of projection. After collision, the ball returns to the point of projection. The coefficient of restitution is. Let's see how to solve this kind of problems towards a vertical smooth wall. See carefully. Whenever questions given like this, projecting a ball towards the wall. So what happens here? When ball is hitting the wall, force by the wall on the ball is only normal to wall, right? That means if you take here velocity components like ux and uy, velocity components, since the force is normal to wall, that means this force is only along horizontal. Vertical component does not change. What is it? Vertical component does not change. That means there is no change in time of flight. So time of flight remains the same. Getting the point. And one more point, maximum height. Maximum height also remains the same because force is along horizontal. That means this is not affecting vertical component of velocity. And we are knowing that maximum height and time of flight depend only on vertical component of velocity. So these two remain same. Using now these key points to solve this problem. Okay. Now see the question carefully. So projecting the ball towards a wall, distance given d, velocity, it is v naught, which is equal to root gh. Condition is that it reaches again the same point, right? Reaches again same point. Then see what we can do here. Using now this key point, time of flight does not change. To reach now wall, time taken is, let us take it as a t1 time taken, which is equal to displacement d, velocity component is v naught cos theta, right? Next, from there to back, while coming back, its velocity becomes now vertically no change, but ux becomes now e times of ux because wall is now second body. So before collision velocity ux, after collision it becomes e times of ux. Now t2 to come back, displacement is same, d same only. It is now e times of v naught cos theta. Okay. Now see what we can do here. Sum of these two must be equal to time of flight. Writing condition t1 plus t2 equal to time of flight. See here d upon v naught cos theta remaining is 1 plus 1 by e. That is equal time of flight. Time of flight is 2 to v naught sin theta upon g. Right? Then see what we can do here. D into 1 plus 1 by e is equal to 2 as usual. V naught into V naught square, and V naught given as root gh. So V naught square is gh. Sin theta cos theta. It is sin theta cos theta. Sin theta cos theta upon g. G gets cancelled. G gets cancelled. D into 1 plus 1 by e is equal to sine 2 theta, right? Sorry, h into sine 2 theta, and I can take d also here by d. So from this, see what I can do. Take 1 by e value. 1 by e equal to h sine 2 theta minus d by d. Therefore, e value d upon h sine 2 theta minus d. Okay. So key point is there is no change of time of flight as well as maximum height. Okay. Using that key point, we can solve the problem.